Imagine you're soaring on your favorite roller coaster, wind in your hair. In the control room below, the processor managing the 3 trains starts to overheat. You cruise right through that block break. Now the processor that controls the critical safety system has gone dead. You're now heading towards a train in front of you, and the processor of the ride has gone silent. Operation scrambles to push buttons and check readouts, trying to figure out what is happening with the ride. What happens in those critical seconds when the ride's brain goes dark? And will you stop in time to avoid an accident?
Now get ready.
Ladies and gentlemen, welcome to the Ryan Ride Mechanic channel. How the heck are you doing today? Alright, today's video, we're going to be looking into what happens when the safety processor crashes on a roller coaster or on a ride in general. So a lot of us think that the fail-safe inside of a processor, we say like, oh, there's multiple processors working so that won't happen. But it's not actually the case. Life safety systems like you would have on modern day jetliners out there, they have multiple processors running the same thing so that if one fails, another one can take right up in its place. Some systems can actually make repairs to themselves while the airplane is still in the air. Roller coasters, rides in general, typically aren't that way. In this video, I'm going to generalize a lot of things and put them together. So we run through a consistent, like this is the average. When we use averages, there's always something above or below. So it can't account for everything. The process of designing a control program for a ride and a control system for a ride is vast. It covers so many components, so many things, so many different trains of thoughts that I can't cover everything. All I can do is kind of give you an average, middle of the road, this is what the industry is doing right in this area. I can't give you the extreme at the top, and I can't give you the extreme at the bottom because the lines get so gray and fuzzy so quick, I just can't do it. So we're going to focus in, and we're just going to say you're riding along a ride, and the processor goes dead. What happens? You want the short story? I'll give you the short story so a lot of people can click off the video early. You're going to be fine. Like, subscribe, share, do all that stuff downstairs. Have a good day. Realistically, the processor on a roller coaster is designed to control itself and the ride. Now, when it goes bad, it is designed to stop. Everything on a ride pretty much is designed to stop. There is nothing designed to continually go unless for some reason stopping that process is going to be catastrophic. The stopping is going to be worse than just letting it go. I can't think of too many instances where that is, but one of those things where rides are typically put in that little gray area, and if you've been an operator of these things, you know this. One of these things is rapids rides. When you start the pumps to a rapid ride and you start that flow, that river, a lot of these troughs are just a couple feet deep of water, but they're moving fast and they're sometimes 10, 14, 20 feet wide. It takes very big pumps to run these things. Depending on the scenario each time, shutting those flow pumps down could have a catastrophic effect where they don't want people to do that. So if you've ever worked one of these rapids rides, you'll find out that there is all sorts of scenarios around not shutting down the pumps in certain specific instances where you don't want those pumps to shut down because the flow of water being lost would be worse than the flow of water continuing. So let's see, when I did my rapids video, I had a ton of people in the comments say, yeah, I was trained never to hit the E-stop here, never to do this. There's plenty of ride stops, there's motion stops, there's all sorts of stops on these rides. But on some of the rapids rides, it was like, yeah, you didn't want to actually press the E-stop because it would drop the pumps out. Some parks actually have rides where the E-stop doesn't actually control the flow pumps. Very rare, but this is one of those little spikes where it's like, yeah, Sometimes things happen like that. Okay, so when it comes to rides in general, what does the processor do? The processor looks at the code it was given, it looks at its real world inputs, and then it makes the decision through the code strands of what to do, the ladder logic on the inside typically used, and then it writes to the real world outputs to tell devices what to do out there. So what happens when that brain goes dead? Well, it simply just stops writing its outputs. It typically does not leave an output on, it just stops everything. It stops solving the logic. So all of your outputs typically on a dead processor will just go away. Now, the processors have steps inside them to verify if the A side and the B side are working properly. In the older days, you would run two processors, one on top of the other, and literally pass electricity from processor A through processor B and let it go out to the ride. The reason for doing that is that if processor A had a problem and it said it wasn't going to let some process happen, processor B wouldn't allow it either. So it was like a safety. It was A and B working together to allow it to happen. Then in the logic, they would crisscross their processor images to double check with what they were doing the whole time. So A was constantly checking what B was doing, B was constantly checking what A was doing, moving the processor images over at the same time and comparing them to make sure they were both operating correctly. In new processors and safety processors, what they've done is they've used an ABC gate check. Very cool little thing. I don't have too much experience in it, but basically what they did is they said inside the processor, inside each little output card, they said the processor is going to run, it's going to tell the signal to turn on, it's going to do it from the A side of the processor, then through the B side of the processor, and the signal should turn on, and when it does, it triggers the C side to say, yep, A, B, and it went through to C, everything's working properly. That card reported back to the main processor and said, yep, everything's working good, we're good to go. What that does is that will actually protect you from shorts internally. This happens when too much current flows through a card for some reason, like there's been a catastrophic failure down the line, a valve shorts out or something like that and causes the output card to basically fry, and it turns itself on and stays on the entire time. Not a good result, but the processor actually watches for that. It makes sure, like, okay, yep, power is turned on, power is turned off, power is turned on, power is turned off. Up the stream further from where that processor is, there's typically master enable relays. These are big relays that allow big current to go through. When the processor encounters a fault, it typically drops out those master control relays. They drop out and removes power from all the other devices. So we monitor the PLC with what? Anyone remember what it was? PLC video a while back, I went over these. We monitor the PLC with watchdogs. We tell them to turn on and off at a certain frequency to make sure the brain is alive. It's constantly like saying, hey, you okay? I'm okay. And then every once in a while somebody goes, hey, you okay? I'm okay. And then every once in a while they say, hey, you okay? And it's like, no answer. And if I don't get an answer back in a quick enough time, the watchdog drops out and it drops out all the master control relays. It says, hey, I asked if he was okay, didn't answer me, so therefore was not okay. That catches those little blips in the cycles. Watchdogs can go down from minutes to seconds to even smaller than that, little tenths of a second, stuff like that, to watch the PLC signal flicker on and off. Sometimes PLCs do that. They give them a flicker. It just looks like a little signal bouncing up and down out of one particular output. And that will actually go over to the watchdog. And the watchdog will just watch that output turn on and off, on and off. And then as soon as it stops, the watchdog goes, whew, problem, shuts everything down. So watchdogs are the first thing. Electrical safeties, you also have relays, interlocking things inside the control cabinet. So, for instance, to let a motor turn on, you might have to have 1, 2, 3, 4 relays in a row all pull in at the same time to allow that motor to actually turn on and run. If any one of those 4 relays are not on, that means some condition's not met. Even if the PLC tells the relay to turn on, there might be something physically interrupting it in the meantime. A scenario where that might be like a transfer process. Hey, we rolled the transfer track over and we're going to put a train away, and the PLC says go ahead and drive the train backwards, but it goes down through 1, 2, 3 relays and the fourth one is not on. Why is that fourth relay not on? Well, that's because one of the track lock switches is not engaged. But the PLC told it to turn on and go backwards. It's like, well, yes, that's the case, but a lot of these switches have two sides to them, an A and B. So on the A side, all the A sides lined up and they said yes. And the PLC said yes, go back. On the B side switches, it started to go through that daisy chain, meaning they're in together. It went 1, 2, and then it went to the third one, and that third switch wasn't on. That's a broken proximity switch, where the A turned on, but the B did not. So on the A side, told the PLC everything's fine, move the train back. But the mechanical side on the B side, that manual circuit went through, and that B side was used to feed that relay. And that relay never turned on. So it did not allow the train to go backwards. We use dual interlocks like that in a lot of different places where the processor has to say, yes, everything is good, but then there's some sort of an electromechanical interlock or a latch between the two that confirms that everything out in that same area is also good. Let it go through. Then we'll step up into maintained relays or latching relays. Latching relays are an older thing used on a lot of old Aero, Vekoma coasters, early stuff like that for block logic. Blocks are components where we allow one train to go into an area that's called a block. Blocks are guarded by brakes on the ends, and that's how we keep trains from bumping into each other. We only allow one train in block A at a time. That's it. It can't go. Two trains can't go into block A. Then once that train goes into block B, we have two blocks occupied, A and B, until that train is all the way inside of block B, and then it resets block A. And then B to C, C to D, however many blocks there might be. So in the older days, we used to use block logic through these controlled or latched relays. So it would go in and the relay would pull down, it would go down to its B coils and suck down, and then the ride would know that there's a train in block B. Now, what's the great part about latching relays is that you could take the power away from the system and they will not change state. They're mechanically latched in the down or the up position, so they don't spring back to the middle. So if I have a train in block B and I lose power, I can roll the train out of block B into block C, into D, and wherever else and move it away. When I turn the power back onto that ride, it will look through and that relay will still show that that train is in block B, and I can't just go over there and say, oh, it's not, and remove it. Now, a lot of times there's confirmation on these things as well. Like a lot of times there is wherever the brake zone is, there's multiple proximity sensors. And if any one of those proximity sensors is flagged or high in that area, that means that block is occupied. So even if you tried to reset the block, it would go right back to occupied because there's a train actually sitting there. And then on the processor side of things, we have the exact same type of latching logic that's used in there, but it's inside the controller itself. So we don't use latching relays, but we use it in the controller where it reads and writes to certain latched files, to where when you turn the power off to that controller, it knows that that bit was a 1 or a 0. And then when you turn the power back on, it goes into its files and into the read-write, and it will take those numbers and it will put it back inside and make sure it's a 1 again, or a 0, whichever one it was. Now, is that foolproof? No, because you can turn the power off and move trains around. So it still does the same exact thing. That's why block zones are littered with proximity sensors all over the place, because that is where the train is going to stop. Could you run into a problem? Absolutely you could. Could you valley a train between the block zones? Absolutely you can, by all means. Can you reset a train when it's between block zones or between proximity sensors in the zone? Yes, you can. That is how Smiler happened. Was between sensors, and they reset the block system, and crashed two trains together. Now, all these electronic devices and mechanical devices rely on what's called their normal or their resting state. So when I look at a switch contact, like here on the emergency stop button, I'm going to use a switch contact on the back, which is designated NC, or normally closed, or NO, which is normally open. The normal, in this case, is what we're referring to in a powered off state. This is when the power goes away from it, it goes to what state. Now that's very important because the first thing we do when we monitor these rides and we see that there's any sort of a problem anywhere that we don't like is we typically take power away to prevent something from happening. But why does taking power away prevent it from happening? Because we've done the engineering and we've made sure that the normally blank is the proper position for it. So when we move into mechanical safeties, what's the biggest mechanical safety we have on a ride? It's this guy right here. This is a brake, right? This is a mechanical safety. So what do you think the normal state of these brakes would be? Well, these would be normally closed. That means with all the power off on the ride, they would be closed. Now, we typically want to engineer a brake to say that when you not only take the power off, it closes, but you also want to make it to where when you take the air pressure away from it, it closes. Now, some brakes don't actually do that. There are still rides out there, plenty of them, that use normally open brakes when it comes to air pressure. For example, this one right here, this is an old Aero/Vekoma brake. When you take the air pressure away from this, it opens. But the engineers did enough in front of it. They put storage reservoirs, check valves, safety valves, and everything else in there to make sure that if you ruptured an airline or you blew the air compressor apart back there, that these brakes would still have 20 minutes of air pressure to operate. And if you took the power down, all the solenoid valves on them would open, which allows air pressure to flood into this brake assembly and shut. So with no electricity, that allows the air pressure through to this, which makes the brake normally closed on a power outage. This is one of the reasons why the industry loves magnetic brakes, because magnetic brakes don't need electricity and they don't need air pressure. They are just on all the time. The only problem with magnetic brakes is they cannot stop a train 100%. They can stop it down to like 98%, but as long as the train is on a grade forward, it will still roll forward. And I know a lot of people always ask, well, why don't you just make the brake one flat and level, and then you can't move it out of there? It's like, well, engineers will actually go so far to the point they'll say if it's really windy, the wind could actually push a train out of those brake areas. It's possible. It's a thing. It could happen. Not likely, but I guess it could happen. So for the sake of engineering, okay, we're going to just leave the brakes typically slanted at a slight angle forward, and we're going to leave a mechanical pinch brake at the very front of it that's acting as the legitimate block brake. On an old spinning ride that we used to have, the trains would go through, it would hold the brakes open all the time. It would hold them open the entire time. But the manufacturer was paranoid that the brake would get stuck open, and they did not want that scenario to happen. So what they would do is hourly, they would test the brakes. It was really interesting how they did that. They took a good running cycle, so where the trains was running just fine, and as the train went through each brake, as soon as it exited the brake, that brake would shut and then open again. And then it would go through the next brake, and that brake would shut and then open again. So every hour, they watched the brake cycle closed and then open again. And that told the manufacturer that the brake was still functioning the way they intended it to, and that when they needed to hit the stop button or shut the ride down, that those brakes would in fact close. Again, those brakes were normally closed. So when you lost air pressure or power, they would close. If you took power away from the solenoids would release the air and the springs would shut the brake. In regards to the scenario at the very beginning of the video, the truth is that if you go along and you're going through the brakes, and as soon as you leave those brakes, that processor just goes dead, every brake on the ride will shut off. Every brake on the ride will close, the lift hill will stop working. If you had restraints unlocked, they will return back to their normal state, which is they will lock back. The brakes will close, everything shuts down. Most of the time, even typically the air gates will close back. They will default to the gates being closed, not open. They won't be maintained. If there's something that's going along, like a safety switch, needs something either not in the fully retracted or the fully extended position, they use it's a safety valve in the middle of it. And this is where it's a 3-position valve. Instead of normally valves work like you give the output air, or you take it away and you give the other output air and you take it away. So it allows cylinders to extend and retract. Safety valves actually have a 3rd position in the middle, which is typically all the ports are blocked. It won't allow air to go anywhere in the system. So this is like, it's kind of like a neutral, but it's not a neutral to where you can move it. It's like if I had the cylinder halfway extended and I suddenly move the safety valve back into the middle, it will just kind of hold that cylinder in limbo right there. It won't allow it to go further one way, but it won't allow it to go back the other way. Just neutral. It stops it right in the center. Now, processor crashes on rides is not an extremely common thing, but it also depends on the ride, who programmed it, how old it is. Like, all these things are just variables into the rides, essentially. We used to have a Starflyer. The program would crash probably 3 times a year. It'd be going up there and it would just, operations would call the ride down. And it's typically, sometimes we get lucky and it was loading at the bottom. And sometimes we wouldn't get lucky and the star was halfway up the tower and people were stuck. And what happened is we go out there and say, what's the error? Because we look for an error code to kind of know what we're dealing with. And they said, we don't know. The screen's all question marks. It's like, oh, kind of like that slide from the beginning of the show where it just went into a blue screen with all question marks. That's what a crash processor looks like. That's where the screen, or the operator panel, HMI, panel view, whatever you want to call it, is looking for information from the processor, and the processor just went dark. The screen has its own processor to display and talk with that information and actually give it to the operator. So the processor in the display said, I can't talk with the other processor, so it doesn't know what to display. So it just gives question marks. So we would show up there and be like, oh, yep, it lost its program. Crap. So we'd have to go into an emergency mode, which is essentially we'd power the ride off and turn on an emergency winch motor back there. And then we would go out to the star and basically manually drive the star back down to the ground. And then we'd have to go through and manually unlock all the restraints, because all this was being done essentially with the power, the main power to the ride, off. So we couldn't use the other stuff. And then once people were off of it and everything was all said and done, we would move the star back up, and then we had to reload the program. Now, this was something that the park could do. We had the tools and information to do it, but not every ride is going to have something where the park can just go up and reload the program to the thing. It still took a while. It still took a couple of hours to reload, because once the program was reloaded, we had to go back through and do all the safety tests and everything else to make sure everything was functioning fine. And then we put like about half an hour of cycling on the ride to make sure everything was also okay there. And then we lost the cycles that it was running for the day. So we'd have to go back to operations and manually track how many cycles it was doing for our purposes of tracking the cycle counts. We've also had a similar scenario on our floorless coaster where it just went up and everything just shut off. Went back, there was no startup, there was no manual mode, there's no auto mode. Those things don't work when the processor crashes. The processor just goes away and it can't do any of the ladder logic functions. So essentially, the thing becomes a giant block of steel just sitting there. And then you have to go out and manually get the people out wherever they are, because you're not going to get them to move after that unless the ride had some sort of really weird emergency generator system where you could manually run the entire thing just off of 3-phase power. But most rides are not set up with something like that. But same scenario, go there, the HMI panel view, whatever you want to call it, that's staring at the operator is just nothing but question marks sitting there. It does not know what's going on. And then hopefully you have all this stuff to not only link up with the computer, the processor, and reload the program. Typically that means that processor has to be replaced. So what's involved in that? Well, they're actually really simple. Luckily for you guys, I keep processors and stuff sitting around. Okay, so this is a cheap I/O card module here. I mean, this whole thing is probably like $400 or $500. It was just off of a different project, but I've got it. So this is the I/O modules right here. This is my power supply. This is my processor. This is a, let's see, syncing. This is an input card. This is a relay output, and then 3 relay output cards. So inputs, outputs. Okay. So this is my processor. I can plug in Ethernet right in the front and communicate with this thing. And if I need to replace it, this one's really easy, and so are the ones I've worked with, like Allen Bradley and stuff. Simply just open up the little clasps on there, and then you just pull it straight out. There we go. That's it. There's the processor. Take it right out. Now, the Allen Bradley ones I'm used to dealing with, and Siemens and those other ones, they're a little bit taller. They're shaped a little bit differently. Depends on what revision of what you're running. But they all communicate off the back plane right here. They all have memory chips and things like that, and there's the processor on the inside. So that's it right there. So you can literally just pull it out and then go get another one and put it back in. I wish it was really that simple. Kind of is, kind of isn't. But like for this guy right here, see that little sticker right there? Says V2.5B. That's a version number. So when you get a new processor, you have to find out what your old processor version was and make sure that the firmware loaded onto your new processor is the exact same as the old one. This can be quite troublesome for a lot of parks where they were using version 2.5B. It's like, great, if I buy a new one, it comes preloaded with version 27.6. Okay, great upgrade, right? No, not quite, because the different versions might store stuff in different areas inside the processor. This might make my program crash or cause catastrophic results that we don't want to happen. So if the park replaces their processor, they have to make sure that it is the exact same firmware version in the new processor as what was in the old one. If you don't have all that stuff, then you're stuck going back to the manufacturer and having them give you some sort of solution. This is not one of those things where it's like, oh, they just manufacture wants money. It's like, nope, manufacturer doesn't want to deal with it either because it's a pain in the butt for them. Installation, by the way, just help to do it straight. Yep. There we go. Processor is installed. As technology grows, the need to pull processors out and replace them and reflash them and all this other stuff kind of starts going down because everything can be done online. You can actually link up with the processor over a network, put a new image into it, do everything you need to, and get out of it completely on digitally, just not even from the same area. So that asks the question, well, can the processor be hacked? It's like, you're not supposed to be able to hack those processors. And the reason for that is because most parks, not all of them, most parks have them mechanically separated from the network. What does that mean? So most of those processors and stuff, the way you talk with them is with an Ethernet cable. That's still preferred with all these stuff, is you just connect an Ethernet cable to it, it puts it on the network, and then you can talk with it. Most parks use a standalone computer that sits right next to the processor, so the techs can actually interface with the ride and see what's going on. See what's going on because you can't actually make changes in those. Remember, this is a black box. This is hands-off. You can't touch these things. The program on the inside, you can't mess with it at all. Life safety. Can't touch it. Only the manufacturer can touch that thing, or a certified, qualified engineer that is well-versed in all this stuff, way above my pay grade. So the part of that there is that the internet connection that you would use to get in there and do that is disconnected. So the ride computer typically does not have an outside internet connection. All the Wi-Fi, all the stuff like that, that is turned off. It's Ethernet only, and the Ethernet cable is typically unplugged from the machine. Or if they want to leave it plugged in and you've got a really cool IT department, then they go off and they just turn the ports off in the back and don't allow anything to come through to those ports. Now, cybersecurity has gotten a lot better these days, so it's not surprising that some manufacturers are leaving their equipment online, but there's still one thing that you can't put online, which is this little tiny switch right here. Most processors out there use a switch, or in a lot of cases a key, to actually switch it between the run and the program. So you need there's a physical interrupt on the processor to prevent someone from going in there and reprogramming the processor. You have to physically be there a lot of times with a key, and you have to put the key in the processor and turn it in order to program it. And then when you're done, you have to take the key back out. That's a lot right there. Most places, like even if you can hack really good and get into a processor, most places you can't turn the key into the program mode while it's sitting there. So most of the time that will stop things. Now, possible, anything's possible. Be ignorant of me to say, oh, it's impossible for that to happen. It's like, no, anything's possible. Just doesn't happen a lot. And most of the time, inside the processor are the editing files, because when you switch that into program mode or you do an edit, editing files are also monitored, which means that in the program, when I'm running my automatic mode, one of the first things I'm going to do way in the startup, way at the beginning of the program, is I'm going to monitor for a force, which where I manually turn something on inside there digitally. I'm just going to force that output on. It's either I'm going to monitor for a force or I'm going to monitor for an edit. And if I see a force come on or an edit come on, that is going to turn my program off. I'm going to prevent the program from running in operation. So it's not going to do that. And it's all the stuff with a PLC. This is the reason why a lot of engineering companies won't go fix other programs inside of rides. Even a lot of times the manufacturer themselves won't go backwards and try to fix part of one of their very old rides, because unless they have the engineer that actually made the original program sitting there working on it, they don't know the original engineer's intent. Because I could write a program and put stuff in there that makes it work one way and it's really special and cool, but it's safe. And I've said, well, this is the safety behind it. Here's all the stuff. And everyone agreed, yep, that's safe. Cool. Then the next engineer comes in behind me and they say, well, I don't know why he made all these separate files in there. I don't know why he put all these bits inside here. Like, that doesn't make any sense. None of this makes any sense. And they just want to wipe it out. Well, that means they just wiped out my safety system. What I said was safe, now they've wiped that out. So now they've unknowingly made an unsafe condition. So it's why a lot of manufacturers won't edit their own programs. Something we ran into ourselves. We asked Intamin to come back and fix one of their pieces of equipment that was, 18 years old when I was there working on it. But it was one of the things they said the only way to do it would be to call back the original engineer who was no longer with the company. And then that was a whole different can of worms. So we pretty much said, okay, program's not going to get fixed. It wasn't a safety thing. It was just some minor little edits we wanted done, like moving timer values and things like that. But couldn't get the original engineer back, so we could not do that. Last but not least, when it comes to that standalone computer where I was talking about where the mechanics can go in the back room and see what's happening, a lot of times that computer back there does not really hold anything on it that's special. It just kind of interfaces with the processor. A lot of times a laptop, something else can do the exact same thing. Sometimes when you have a third or fourth party system in there, that computer might hold a program that talks between the two. So the ride might say, hey, there's a problem with the drive system, and that computer might be able to link also to the drive system to say, here's what your actual problem is. But that's an older mindset, and these days the drive talks directly with the PLC. The same problem can happen with the drive. Its processor can just die right in the middle of things. Same exact thing. It loses its healthy feedback. The ride instantly shuts down. It kills all the power and everything. Again, everything on these rides is pretty much designed to stop. That's what's going to happen if you lose the processor. It's going to stop. and it's designed to stop in safe places. So you won't have a problem with it. All right, I've done enough on this video. Like, share, subscribe, do all that stuff. It helps me out. If you want to watch another video, I do appreciate it. If you want to contact me, you can always leave a comment down below. You can email me at ryantheridermechanic@yahoo.com. As always, stay off the air gates.